I am Seshagiri Rao, Associate Professor in the Department of Electronics and Communication Engineering. Today I am going to talk about the design approach for PROM, PLA and PAL and in the VLSI design subject. PROM, PAL and PLA, they belong to the class of PLDs, Programmable Logic Devices. You know, we have ICs of 74 series for NAND gates, NOR gates, multiplexers, encoders, etc. So those ICs, the functionality is fixed. Suppose you take an encoder IC, it does only encoding. If you take a multiplexer IC, it does only multiplexing. NAND gate IC, it does only NAND operations. So the functionality is fixed. But suppose the same IC you want to use for different applications or different programs, you have to introduce the element of programmability. That means if you take an IC and if you introduce the programmability feature, you can use the same array of NAND gates, NOR gates which are present inside the IC to function as encoder or decoder or multiplexer or demultiplexer. So the programmability, it enhances the flexibility and you can use the same IC depending upon the requirement. The PLDs, there are three types: PROMs, PALs and PLA. So PLA means Programmable Logic Array, PAL means Programmable Array Logic, PROM means Programmable Read-Only Memory. And these devices, they contain an array of AND gates and OR gates. And we are going to follow certain conventions. The conventions are, suppose we have a 3-input or 4-input OR gate. So these are the 4 inputs. We have 1, 2, 3, 4. These are the 4-input OR gate. So this is, we are going to represent this in this way. So these are the 4 inputs: 1, 2, 3, 4. These are the 4 inputs. And similarly for AND gate also we are going to follow the same convention like this. Suppose we have a 3-input AND gate, then these are the 3 inputs: 1, 2, 3. These are the 3 inputs. And when 3 inputs are used, I am going to use a link here. So that means there are 3 connections and this AND gate has 3 inputs. So this is the convention what we are going to follow. Now the first category of PLDs is PROM. So the PROM contains fixed AND array and programmable OR array. That is the structure of PROM. So when you have a fixed AND plane, it functions like a decoder. Suppose you have a 3-input decoder. So how many AND gates are required? You have 8 AND gates because there are 8 combinations: ABC, ABC bar, A bar, B bar, C, like that. So we have 8 combinations. And the next OR plane, it is a programmable OR array. Okay. Coming to the PAL, in PAL we have the programmable AND array and fixed OR array. That means only the AND plane is programmable and OR gate is fixed. So that is a programmable array logic. And coming to the programmable logic array, in programmable logic array, both AND array and OR array, both these AND and OR planes are programmable. So depending upon the Boolean function which you have to realize. Okay. Now let us see this. Here we have a programmable read-only memory. So as we told, this has three inputs, and we have 8 different combinations: A bar, B bar, C bar, A bar, B bar, C, and A bar, B, C bar, and ABC. So when you have three inputs, we have 8 possible combinations, and each of the inputs is available. Its complement also is available. So this is A, and this is A bar, and this is B, and this is B bar, this is C, and this is C bar. So, and this is the R array. Okay, so it is a fixed R array. So we have 8 possible combinations. That means to say, in PROM, the AND array plane is nothing but a decoder, and this is a programmable R array. So depending upon your Boolean function, the programming is done by retaining the link. These are the fusible links. What you are seeing here in crossbar, these are the fusible links, and depending upon the Boolean function, the fusible link can stay, or you can blow out the fusible link. Here we have 4 possible Boolean functions: y3, y2, and y1 and y0. 4 possible Boolean functions. So this is a fixed R array, and this is the programmable R array. Okay. Now let us come to the programmable array logic. In programmable array logic, we have the programmable AND array and fixed R array. You can see here the AND OR gates, there are 3 inputs. Each OR gate has 3 inputs. So the representative, each input is available in its original form and also in its complemented form, as mentioned here. Next, the output comes. Here we have, this is a typical programmable array logic. In actual practice, it has many more inputs and many more outputs, and this is just a representative form of the PAL. In actual practice, the PALs are more complex, and this PAL, what is shown here, it has 4 inputs: A0, A1, A2, and A3, and this is the A3 is in A3, and this is A3 bar. That means the input is available in complemented form also. And these are the AND gates, and we can form Boolean function in sum of products form. Okay. In the first array, which is giving the output D0, you can see the output is fed back to the input. There is a provision for feedback from D0. So you can, here you have D0 and D0 bar. So and there is no provision, the feedback provision is not given for D1, D2, D3, and this has some advantages, as we are going to see in the example what I am going to demonstrate. So each AND gate, it has, along the horizontal line, it has 10 programmable input connections. So there are 10 programmable input connections because you have 4 inputs. That means 4 inputs means 8 inputs because of complemented form also, and because this D0 is fed back to the input, and D0 and D0 bar also is available. So there are basically 8 inputs. Now let us take this example. W is equal to sigma m 2, 12, 13, and x is equal to sigma m 7, 8, 9, 10, 11, 12, 13, 14, 15, and y is equal to so and so, and z is equal to sigma m 1 to 8, 12, 13. So how to realize the Boolean function using PAL? So that I am going to discuss now. You have to use the K-maps to minimize the Boolean function. K-maps are used to minimize the Boolean function. When you minimize the Boolean function, it uses minimum gates, so it results in a reduction of hardware. Now, Let us see how we can minimize this function. For example, I will take x. X is equal to sigma m 7, 8, 9, 10, 11, 12, 13, 14, 15. Of course, minimization you are already aware in switching and logic circuit design. Now let us see how you can minimize this x. See, you have numbers up to 15. That means you need 4 variables. So let us call this as AB and this is a CD. So this is 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Okay. So this corresponds to decimal number 0, 1, and this is 2, this is 3, 4, 5, 6, 7, and of course this is 8, 9, 10, 11, 12, 13, 14, 15. Now I am going to show you the simplification for x. Okay, so this is the I am going to show you the simplification for x. So x contains what? 7, 8, 9, 10, 11, 12, 13, 14, 15. That means from 7 to 15. All numbers are available here. So 7, 8, 9, 10, 11, 12, 13, 14, 15. So all these numbers are available. So K-map simplification, how you do? So you have to form one array here and another is this one, right? So what is x? X is equal to, this is 1, 1, 1, 0. So A is common. So you call this as A, right? And coming to this quadrant, what is common here? The common here is B is common. So called as B. And CD are same, so BCD. So x is equal to A plus BCD. So this is similarly you simplify W and Y and Z. So all these things you simplify. So here W is equal to ABC bar plus A bar, B bar, C, D bar. So you see here this is W. So ABC bar. So I am going to retain this link A, B and C bar. So these links are being retained and other links are blown out. So these links what I have marked in red color, these links are going to stay and other links are blown out. So this will give me A, B, C bar. This will give me A, B, C bar. Okay, and this is A bar, B bar, C, D bar. So you see here A bar, B bar, C. So I am going to use C and D bar. So all these 4 inputs are programmed accordingly, and this will give me A bar, B bar, C, D bar. Okay. So W has only 2 products, A, B, C bar and A bar, B bar, C, D bar. Okay. So this AND gate is not used because W has only 2 terms. Okay. So that is why I have marked it into here. That means this AND gate is not used. So I have realized W. Similarly, X is realized and X also has only 2 terms. So this AND gate is not used. This AND gate is not used. And Y has 3 terms. So all 3 AND gates are used. So this is used, and this is also used. So I get Y. Now coming to Z, see Z has 4 terms, but I have only 3 AND gates. So how do I go about it? How do I go about it? Z has only 3 AND gates, but I have to include 4 terms. So what are the 4 terms? A, B, C bar, A bar, B bar, C, D bar, A, C bar, D bar, and A bar, B bar, C bar, D. 4 terms I have to include. And you see here, this A, B, C bar and A bar, B bar, C, D bar, it is nothing but W. What you have seen here, it is nothing but W. So I can write here Z is equal to W, A, C bar, D bar, and A bar, B bar, C bar, D. So now Z is having 3 terms. Now but one of the inputs is the function, earlier function itself, W. So that is why this feedback path is used. This feedback path is used to form one of the inputs. So conveniently, what I am doing for Z, so I am using this W and W bar. Okay. So I have written here Z is equal to W, A, C bar, D bar, A bar, B bar, C bar, D. So I am using W, and I have this W which is coming back to the input, and this I am using here. So I am able to use 3 AND gates comfortably. So Z is equal to W and A, C bar, D bar. So A, C bar, this is C bar and D bar, and this is A bar, B bar, C bar, D bar. So accordingly, I have programmed the fusible links, and I have realized the Z using PAL. So PAL is programmable AND array and fixed OR array. So in OR gate there is no programming. So this is how we can realize a Boolean function using PAL. Coming to programmable logic array. In programmable logic array, both AND plane and OR plane both are programmable. And PLAs are available in different forms. Actual PLAs are more complex in nature. Now, in the PLA, what I have shown in this diagram, it has 16 inputs. So you have I0 and I1, so and so, and I15. There are 15 inputs, and there are 48 AND gates. So you have here P0, P1, and P47. There are 48 AND gates and 8 OR gates. You can see here there are 8 OR gates. 1, 2, and so and so, and there are 8 OR gates and 8 exclusive OR gates also. These are the 8 exclusive OR gates. And this the use of exclusive OR gate is it provides the function in its original form and also in its complemented form. So that is the use of exclusive OR gate. So in what way it is exactly useful, I'm going to show it using an example. And final output is tri-stated by chip enable. This is the chip enable signal, and the output is this can be disabled by using this tri-state facility. That means the outputs can be in high impedance state if chip is not enabled. So this is also referred as 16 into 48 into 8 PLA. 16 into 48 into 8 PLA, because there are 16 inputs and 48 AND gates, and you have 8 OR gates. The difference is in PLA both AND gate and OR gates both are programmable. That means both AND plane and OR plane both are programmable. Programmable facility is provided by using the fusible links. If you need a connection, the fusible link is not disturbed, otherwise the fusible link is blown out. Now let us see an example of realizing a Boolean function using programmable logic array. Now here we have a function f1 which contains the minterms 2, 4, 5, 7, and another function f2 which has the minterms 0, 1, 2, 4, 6. Now, how to realize this Boolean function? Let us see. Okay. So F1, you get F1. You see here. This is 2, 4, 5. This is 2, and you have here 4, 5, 7. So this is the K map for the F1. So F1 is equal to A B bar plus AC plus A bar B C bar. So this is how you get the function. Okay. Now the another function 0, 1, 2, 4, 6. Okay. So how you are going to get? So this is A and BC 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. Okay. So this is 0, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7. So the F2 is what? 0, 1, 2, 0, 1, 2, and 4, 6. 4, 6. Okay. So there are so many terms. So as you see here, you have to combine these two, you have to combine these two, and you have to combine these two. So much minimization you have to do. And what is the, so I'm going to use the exclusive OR gate conveniently so that I realize the function using minimum hardware. So instead of using the zeros, I will use, instead of using ones, I will use zeros. So zeros are, how many are there? There's 0, 0, 0. There are 3 zeros. So if I use these 3 zeros, what is the function I'm going to get? I'm going to get function in F2 form, because I'm using zeros. So F2 bar is equal to what? AC plus BC. AC plus BC. And later I will use exclusive OR gate to realize F2. So this is what the technique what I am going to follow. So F1 is equal to AB AB bar plus AC plus A bar C bar. So here this is F1, which will come by appropriate programming, and here I am going to get F2. And what is F2? This is F2, and F2 is nothing but AC. F2 is nothing but AC plus BC. So AC plus BC, it will come here. So you will get here F2 bar, and because one of the exclusive input OR gate, I am going to make it as 1. So I will get the complement of F2 bar. So that means I am going to get F2. So this is how I can use the exclusive OR gate provision. Okay. So that is example of realization of Boolean function using PLA. Now let us realize two functions using PL. So here F1 is equal to x1, x2, x3 bar plus x1, x2 bar, x3, and F2 is equal to x1, x2 bar plus x1, x2, x3. So x1 and x2 and x3, and PL means you have fixed R array but programmable AND array. So this will give me this will give x1, x2 and x3. So that is available here, x1, x2, x3, that is available here, and P2 is, so you see here x1 bar, x2 and x3, which is nothing but F1. Similarly, F2 is x1 bar, this is x1 bar and x2 bar. And P4 is nothing but x1, x2 and x3. x1, x2, x3. So this is f2. So this is how I can realize different Boolean functions using programmable logic devices. Next, let us realize the JK flip-flop using PLA. See, to realize any Boolean function, basically what is required is you require truth table. To realize any Boolean function, what we require is the truth table. So this is the truth table for the JK flip-flop. JK, and you have the present input, the present input and the next output. So when all are 0, 0, you get output as 0. Okay. When it is 0, 0, 1, you get the output as 1. Next, 0, 1, 0, you get the output as 0. And when it is 0, 1, 1, you get the output as 0. And when it is 1, 0, 0, when it is 1, 0, 0, you get the output as 1. And 1, 0, 1, you get the output as 1. And 1, 1, 0, also you get the output as 1. When you have all ones, you get the output as 0. So this is the truth table of JK flip-flop. What is it for? And you realize you simplify the truth table using K-maps. There are and this how you can simplify So this is JK, and this is QT, and this is 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, and you have ones here 1, 1, 1, 1, and remaining things are zeros. So when you simplify, you get this is the output, this is our K-map for QT plus 1. So QT plus 1 is equal to QT plus 1 is equal to JK bar plus K bar QT. So you combine these two, you get JQT bar plus you get K bar QT. So this is how you get the function. So now you realize it using programmable logic array. This is J, K, and QT. And their complement form also is available here. You have programmable AND gates. So first is J Q bar T. So this is J Q bar T. So I'll put one more connection here. So here I get J QT bar. And this is K bar. So I'll put one cross here and QT. So I'll put one more cross here. So here I get K And this is the programmable R array. And I need this input, and also I need this input. So this will give me Q, T plus count. So this is how I can realize JK flip-flop using programmable logic array. And programmable logic array, you can realize it using PROM also. What is PROM? PROM contains PROM contains fixed end plane and programmable R plane. So you can realize the JK flip-flop using the PROM also. So how you realize this is 1, 2, 3, 4, 5. Now I'll show you how you can realize it using the PROM. So I will use 3 into 8 decoder, so which will give me 8 outputs. So the decoder is nothing but a fixed end plane. So this is realizing JK flip-flop with PROM. Okay. So I'm going to use 3 to 8 decoder. So how many inputs it has? It has 3 inputs. What are the inputs? J, K, Q, T. J, K, Q, T. So these are the 3 inputs. And it gives 8 outputs. 0, 1, 2, 3, 4, 5, 6, 7. So there are 8 outputs. Okay. And this is the fixed R array. And this has provisions from all 8 inputs. 2, 3, 4, 5, 6, 7, 8, like that. Okay. Three, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. Okay. So all the 8 outputs from the decoder are connected to the OR gate, and there are fusible links. There are fusible links, and I am going to use only this link, and also I am going to use 0, 1, 2, 3 I am not using, 2, 3, 4 link I am using, 5 I am using, and 6 I am using. Okay. So what I will do, 0, 1, 2, 3, 4, 5, 6, 7. Okay. So I am going to use only this link, and I am going to use this link, and I am going to use this link, and I am going to use this link. And remaining links are open. So this is open, this is open, this is open, this is open. Because only output is there from the outputs 1, 4, 5, 6. So programming is done in the OR plane. And as far as the underplane is concerned, it is fixed. Decoder contains an array of AND gates, and decoder is functionality is fixed. It is like a fixed AND array. So this is how we can realize the JK flip-flop using PLA. So we have discussed today about the concepts of the PLDs. PLDs are available in 3 categories: programmable read-only memory, and programmable array logic, and programmable logic array. So with this, I conclude today's session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.